Organic chemistry is a long-haul process. So the way this course is designed is first we look at effectively just drawing representations. What are we looking at? So that you understand what those structures are. We aren't looking at meaning necessarily, but we're looking at what they are. Can we come up with ways to classify and pattern and organize them based on certain things that we see? Those patterns and recognitions become important when we talk about chemistry behind them. Okay? But at this first stage, it's really just what are the representations that we can look at? How do those pieces fit together? How can we draw those things out? That's all we really care about. So again, our structure or our process for the class is structure. How do we draw when we talk about organic chemistry? The next unit is how do we know those structures exist? That's spectroscopy. It's very lab-based. Okay? And then it's, now that we know how to draw this stuff, what happens when these things come near each other? What are the chemistries that start to come out of those functional groups? Those chemistries are things we will allude to as we're moving through. When we look at a drawing, we can say, well, there's difference in electronegativity here. That difference in electronegativity causes partial charges. Why do those partial charges matter? Well, if I have a strong negative, what would I expect it to react with? A positive. So if I start to be aware not just of the structure, but now how those positives and negatives can shift through those structures, when we move to the next part and now actually talk about reacting, that becomes kind of an interesting state, right? A potential analogy that I was talking with a student in office hours about was looking at money. You could look at how money in your house moves around. Right? You could store the money in the bank. You could store it in,
Piggy bank.
what is that?
Piggy bank.
Piggy bank. You can put it in your mattress. Right? That's the money that you control. We're concerned about where that money goes. Does anybody store their money by taping it to the window? Some people laughing, they're like, yeah, I did. No, that's an awful way to store our money. That's a bad process. That's not a good structural way to hide or keep your stuff. Okay, we don't broadcast that to everybody. Right? That's this first unit. Where do we put the money within our house? Right? We could then look at the next unit as saying, well, this is where that money is stored. These are why we know those would be good places to store. So if we were going to be robbers going into the house, we're going to look for the piggy bank. Okay, we're going to look under the mattress because that's where I would expect that money to be. The rest of the units are now, what do you do with that money? Do you go buy a car? Do you buy food? Do you buy for the physical space that you actually live in? How does that money interact outside your house? And depending on how it shuffles around and manipulates within the house, that's going to affect how it moves outside of the house as well. So we have to understand that initial central point first before we start moving outwards. Okay? All analogies fail at some point, and that one's not the greatest, but I think it does a somewhat decent job. Okay? Ivan.
How do you know to read a molecule structure left to right or right to left?
Good question. So if we were going to look at an individual compound, in particular, there's a couple ways we could look at it. This slide will actually do it perfectly for us. Should we be looking at, say, this completed structure in the upper right-hand corner? Should we be reading that left to right or right to left?
Could it be read both ways?
It can be read both directions. Okay. One of the statements that I made a couple times last week was what? There is no up, there is no down, there is no left, there is no right. Okay? That makes things really challenging to answer a question like this. Okay? Organic chemistry is about a three-dimensional world and how that three-dimensional object manipulates and interacts outside it. So we don't have a left, right, up, down. When does a left, right, up, down appear? Because naturally it will. How do you read? Do you read starting at the top or on the bottom? Or on the right or the left? In the middle?
Top left.
Top left. Then what do you do? Left to right. Then you move down one left to right. Down one left to right. So the way information is presented when we talk about a text system is left to right, top to bottom. Okay? That's instantaneously going to clash with organic chemistry, because organic chemistry does not have a frame of reference. It's entirely moving around and shifting. The frame of reference only comes into play once you have locked it in. Okay? So why does this matter? Well, if you look at a test, is a test a three-dimensional object? No. It's very much a paper physical object, which means you will have to read it left to right. Which means what ends up happening is we take this nasty three-dimensional world and it somehow gets translated into a two-dimensional space that naturally has to carry this left to right pattern behind it. So how do we know, looking at a structure, how we should be interpreting and building that into, say, a formula? Well, why do I need a formula? Why don't I just draw the structure? How many of you find it easy to draw the structure? Okay, that was a smattering of hands, and by smattering, 0 hands. So you all think it sucks to draw structures. But can you write a letter and a number, a letter, and yeah, you've had practice with that. So that translation of writing a formula, you go, oh, formulas are great, they're easy. Formulas are horrendously unspecific, okay? Which makes it difficult to actually interpret what that three-dimensional structure is. So what we try to do is come up with a blend between those. Okay, well, why use a formula at all? How do we transfer knowledge? Through a written document. Okay, which means that written document is naturally going to have this left to right process, so we have to come up with ways to interpret it. Okay? Some of those ways are now going to be built into what we've already kind of established within our bonding patterns. This is why the bonding patterns are so important. You need to know the common bonding patterns so that you can interpret a structural formula into a drawing, okay, for an actual compound. Okay, that takes a little bit of practice. It's ultimately an archaic method because it relies on typing. Okay, well, typing's always going to be here. Computers will always be here. But what I would argue is within 10, 20 years, we're not going to be typing our structures, we're going to be drawing them. Because we can now draw with such fluidity and ease that it is easier to draw the compound than it is to write the formula or name it. Okay? Which means you're stuck in a crappy gray space. That gray space where you have to both know nomenclature and formulas and drawings. Okay? That space is going to exist for a while. Okay? That's what happens as technology changes. It's always going to switch on you. Okay? Everybody's going to have a gray space. Okay? So, is that a question?
Sorry, no, we're still going over this.
Okay. So I was going to say, how can we convert that upper right hand into a formula?
One piece at a time.
Okay, we could do that. I could go through and say it has C4H10. 10. Okay, that would work. Okay. I don't want to draw all the hydrogens, just assume those lines end in hydrogens. The structure I just drew in red, what formula does that have? C4H10. That formula, that nice dandy formula that was so easy for me to write, results in 2 different molecules. Do those 2 different molecules have different properties? Yeah. I'm going to feel bad about this. It says ASU on it. I'm going to feel bad about it, but I'll uncrumple it in a second. We got a sheet of paper, right? This sheet of paper can stack neatly on other sheets of paper. Right? This is that red drawing. Nice and flat. What's the top drawing?
3D.
Exact same amount of material, but I've now changed the space that it exists in. Is that going to have a different interaction with the world?
Yes.
Okay? Yeah. Because what do we do when we crumple things up? It's now a ball, and I can throw the ball, and it moves through the air, where if it wasn't crumpled, still legible, promise. And I tried to throw that at a trash can. That wasn't very useful. So the three-dimensional orientation of those atoms in space become a really important deal. And so we have to be aware of that. I'm sorry about that. It's officially recorded, I said sorry. Right? So how can we change our formula so that we could go through and differentiate between those two? Right? Parentheses could change. Well, what do you mean? So that top one, we'll call it the black one, is this?
I'm gonna cheat. I went over your video, so I have it right here.
Okay. What do you think the formula is?
Parentheses CH3, parentheses 2, CH2. Oh, I'm missing CH. Yes.
You gave me a funny look. Why'd you give me a funny look?
Oh, I just feel like that indicates that would be on the first carbon, right? Or no? Because it would be like, what, 2-methyl propane?
Right? Trying to piece this together, now you're dropping in nomenclature into it. Yeah, that's this week. Slow down. Let's go back to last week. Okay? What does that mean? Okay, this becomes challenging. So you have a parentheses around a CH3. Okay, so let's find a CH3. Where is there a CH3 in this top one? We'll go with that black. Where do you see a CH3?
The top, the left, and the right.
Okay, which is taking it to the next level, which is awesome. I overlapping it in black was stupid. Okay, I see a CH3. I see a CH3. I see a CH3. How many CH3s is that?
3.
How many parentheses is that?
3.
How many parentheses did you say?
3.
Come on now, you told me to write 2. Okay,
So then it's parentheses CH3 and then 3CH.
so how do we convert this formula? Well, we can look at those ends and acknowledge that we have CH3. We had 3 of them. What are those 3 CH3s connected to?
CH.
A CH, and we've now represented the structure in black. How is that different from the structure in red, which might be maybe where you were going?
I was looking at one that had one more CH at the very end, actually.
It's okay.
But let's take the photo.
I see 2 CH3s here, right? Can I group them?
Yeah.
This becomes the hard challenge. I can group the black ones because what are the black ones all connected to?
CH.
Take it a step further than that. It's not just a CH. The same CH. Are these CH3s connected to the same CH2? Nope. Which means can't group them. So I could write this as CH3. What CH3 am I representing the instant I've written that down? Play a game of hot or cold.
Couldn't it be the left or right?
Could be the left or right because it is a symmetric molecule. Okay, but how do we read? Left to right, which means more than likely when we look at this formula, we're interpreting it left to right. Could it be either? Yes, unfortunately. Okay, what comes next after that CH3?
CH2.
A CH2. I'm going to come back to that. What comes after that CH2?
CH2.
What comes after that CH2? CH3. So what we're saying is we just connected those pieces. This red formula is now not going to be confused for the black one at all. Right? Okay. Could I change it further?
Yeah, parentheses around CH2 and then a 2.
When I used the parentheses up here, it was because they were connected to the same atom. Are those CH2s connected to the same atom? Not at all. Why can I use it here?
Connected to each other.
They're connected to each other. So how would I know to build out to get to this? That becomes now the reverse logic. Okay? So now we'll do this way. Whoa, now we got to go to the structures. You already know what the structure answers are, right? The answer should be yes, because they were right there, right? Yes, we do. But we just erased them to make it harder. Okay, let's take a look at the one in black. What do I see? It's the first thing I encounter.
3 CH3s.
No.
Parentheses?
I encounter parentheses. How many parentheses do I encounter?
3.
3 parentheses. Okay, what are those parentheses connected to? CH is technically two atoms. Those parentheses cannot be connected to two atoms. They can only be connected to one. So I would argue you shouldn't be saying CH, you should be saying C. Okay, so I've now built those connections. What else is that carbon connected to? There's that other H. So I understand the simplification behind what you were trying to say, but if we're going to try and get more specific, what's in the parentheses? Come on, pen, work with me. That's not an A, that's a H. CH3. Was that the structure we drew?
No. Whether the section, yeah, sorry. Yes and no, but.
Yes and no. Yeah, I had to think through it and remember what was up there initially. Initially, we had the CH3, I believe, on the far right. Okay, well, why is this one the same as the other one? All we did was we took the molecule and we just rotated it. Okay, that's that three-dimensional reality. We have to be aware of that three-dimensional reality, and that's going to come back and haunt us. Okay, again and again and again. Okay, what happens with the red one? Okay, what do we encounter first? A C. What's connected to that C? 3 hydrogens. Does it satisfy its octet? No. So bonding patterns, it has to have one more bond. What's it bonded to? Careful. Careful. Parentheses. Okay. And I really want to do this, and we'll see why, because our rules would all of a sudden go way out the window, right? Because we do the parentheses. How many parentheses should be bonded? 2. So shouldn't I do this?
No, then you break the octet rule.
So if I'm aware of my bonding patterns, I know that those parentheses don't mean they're both connected to the carbon. What those parentheses mean is they're now connected in a line. Bother, I have to know. Yes. This is why it's so important to know the common bonding patterns. Because if you have those common bonding patterns, you could tell right away that that's not going to work. Okay? Which would give you a second to pause and be like, whoops. The whoops was for something else. What's in the parentheses? A CH2, which means I'm putting a carbon there. Why am I not putting a hydrogen? And then the carbon. Hydrogen can't exceed that octet. It's only happy at 2, which means the carbon must come first. We drop in the carbon. There's that hydrogen. It's a CH2, right? Well, hydrogens are next to hydrogen, so shouldn't I do this? No, again, bonding patterns. It has to go to the carbon. Bonding patterns. Carbon needs an octet, which means it has to have another bond. What's it bonded to? I kind of accept the carbon. It's the other parentheses. The other parentheses was my second of my CH2s. What's then connected to the second of my CH2s? Because again, I'm missing that bond. And now I get my drawing. Does that suck?
Yes.
Yeah, I agree. Okay, this, I'm not sure I want to get in that picture.
You're good.
Okay. Okay, this is looking at your kind of formulas or condensed formulas. There's a variety of names for them. They're ultimately an artifact of having to type this information out, because drawing these structures is too challenging to do within a typed document. Okay? And for those people who have iPads or other technology, it's not that hard. It isn't, and it is. It's progressively getting easier, and the point that it reaches the aspect where everybody goes, oh, this is easy, why do I need to type this out? That's the instant the technology goes away, and we don't have to worry about those condensed formulas. But you need at least the average population to agree with that statement. Okay? And it's really easy to get people to agree with each other, right?
No.
Okay, you already disagree with me. Okay, so that's kind of the problem that we have to deal with. This is why you need to be able to deal with interpreting these things, and you'll notice that as we interpreted them, okay, all the way back to Ivan's initial question, where do we go, left, right, up, down, these will always get interpreted left to right. okay? Because they're a left to right format. Structures get no interpretation. The only reason we need to worry about a left-right is if I'm going to convert it back to a formula. Well, why would you ever convert the structure back to the formula?
Test question.
So that you can type it out. Well, you're never going to type it out, so why do we need to ask it? It's dealing with that test question aspect. Do you understand the interpretation from one way to represent that molecule to another way? You have to have the fluidity there. This fluidity isn't a big deal. The fluidity going from those drawings to that, or to that, is a very big deal. Okay? You need to have very fast interpretive skills to go back and forth there. Going out to the formula, yes, it's going to burn you. It will absolutely burn you on some questions of an exam. Is it going to be every question? No. Okay? But it will show up, so you need to have some kind of passing knowledge of it. That's why you see questions built on it. Kind of, sort of? Think I answered your left or right.
Oh, so I should have been more specific. I was actually
Damn.
referring to the nomenclature, like the sense.
Dealing with nomenclature, which you also brought up. You can see how much I like it. I have no preference on nomenclature. But I do at least have one here on interpreting left to right. Nomenclature is, again, a typed format, which means you are going to read it left to right. Does that mean your answer, say in a list of multiple choice, going to show it left to right? No. Because structures have no left, right, or up, down, which means you have to be able to convert, at least initially, a given name into a structure, and then to be able to look at your answer choices to say which of those align. So for instance, if we were to go through and process this, right, and if you haven't seen nomenclature, that's okay, but two of you have at very least, or have some passing knowledge of it. Okay? Where do you take a swing at this? Do you want to take a first stab?
Yeah, so the method is like one.
I'm going to say false. Where do you take a swing at it?
So you would realize that it's 5 carbons in a ring.
Okay, pause. Okay, yeah, and you're good, you're good. I just want to interrupt. Okay, so if we look, okay, I haven't started immediately left to right. Okay, I had your name and it just disappeared. What was your name again? Josh. Okay, Josh didn't look at that. He immediately said 5 carbons and he even said ring. So he started to make multiple interpretations. Where did your 5 come from? Pent. Pent means 5 carbons. You are required to know some language conversions on those processes. The nomenclature video addresses this big nasty slide that covers all those pieces. What's the next thing you said?
Cyclo is ring.
Cyclo is ring. You want to tell me where you would go next? See if I agree with you?
So you know your ene is going to be an alkene, so that's double bonds, which would now be between 1 and 2.
Whoa.
And it doesn't matter
Whoa,
which
whoa,
direction
whoa.
you go.
Jiminy, Christmas. You made wait. Because I looked at it, had a moment of panic, and then I realized technically I did something wrong, but okay with this name. So you have an alkene, okay, which means he's addressing a functional group. So there were some questions about what do I need to know of the functional groups? Well, you need to be able to look at a functional group and identify it at this point. Okay, why do you want to identify it? Because we care about its chemistry later on. Right? Why do you need to identify it? So you can name it. Is naming a good, useful thing? Not really. Okay? But you're responsible for that. So you have to acknowledge and have the basics behind it. Okay? I would argue it. You said between 1 to 2. I accept that. Where do you want to go now?
And then you can apply the methyl group on atom 3.
So what does the methyl mean?
It's just a single CH3,
So 1 carbon.
and then 3 hydrogen because of the bond to the other carbon.
I'll come back to that in a second. Is there something else in our name here? What's the 3?
It's on the third atom, the third carbon, so you have 1, 2 for the alkene, the
We'll
double
call-
bond, and then on the third atom, it'll be the.
We'll call that a locator. So does everybody know what the structure looks like?
Wait, the, one carbon from the methyl is on the third atom?
So you don't know what the structure looks like?
No.
Yeah, okay. Okay. What I would argue is the interpretation he's done is great, and I would start to hint that either you've watched a whole lot and done a little bit of practice, or you've had some background practice with this, which is okay. Right? It takes time to process through this. Each of these interpretations is where I would start to draw something. Before I started drawing 5 carbons out as a straight chain, I would look for that cyclo so I could identify that. Because I've got cyclo in 5 carbons, I would immediately start to draw a cyclic structure, so a ring with 5 carbons in it. Okay? How do I choose to go through and draw that? Okay? Problem with rings is there a left or a right. Okay? And that's where we run into this issue with left-right stuff, is that immediately rings throw everything out the door. Okay? So what we could go through and do is draw a ring. Do I want to draw hydrogens?
No.
Why not?
It's a lot of work,
Because they're black.
and they're not important.
Nobody cares about them.
I'm gonna draw them. If you're drawing them, don't. This is my pain. Okay, so what I've interpreted so far is ring and 5 carbons. And here's where we're going to encounter the next part. The ending of the name becomes the important aspect. The end of the name becomes the big, big picture thing. That's the reactivity of the molecule. So I want to know that part. Okay, which is interesting. That's the end of the name, but that's my primary focus now. We said it was an alkene. Dang, I already forget. Josh?
Yes.
Don't answer. What's an alkene?
It's one of our functional groups.
Nice. What does one of our functional groups look like that represents an alkene?
It's a carbon connected to something else.
Okay. The point here is to address that maybe we're missing some pieces and we need to start backfilling and ensuring that we've got those pieces. Okay? That kind of stinks, right? We're going to feel behind always, but that's part of this process. An alkene is a carbon-carbon double bond. Well, I've just drawn a bunch of carbons, okay? And to the useful aspect behind this, we said it's between carbon 1 and carbon 2. Where's carbon 1?
Anywhere.
Pick a spot.
Anywhere. Since it's perfectly symmetric, it doesn't matter where I place it. Okay? Just to be obnoxious, actually not to be obnoxious, will be nice. I'll stick it on right here. Okay? That looks kind of left and top-ish, right? So we'll go to that carbon. So that alkene information I now want to specify. There's my carbon. There's that carbon. I want a carbon-carbon double bond. I'll now draw the double bond. Before we launched into the alkene, I asked a question. What was the question I asked? Should I draw the hydrogens?
Yes.
Right? And the general consensus was we don't want to draw them because they're useless. They aren't useless. They're actually very, very important, and we do need to be aware of our hydrogens. Was it useful to draw the hydrogens when I did? Yeah? Tell me how many electrons are around our topmost carbon.
10.
10. Can I exceed the octet? No. By drawing in all of those hydrogens, I immediately removed the ability to properly interpret the functional group. Don't draw all the hydrogens in at the very beginning. If anything, we can imply them and leave them out. We do need to be aware of their presence because it does change some of the chemistry, and that presence of the hydrogen will haunt you, both in exam 1 and every other exam afterwards. So don't lose track of your hydrogens. So to properly fix, we need to get rid of 2 hydrogens on the carbons of our alkene. We good? Cool. I've addressed the ring, 5 carbons, and the alkene. I now have this locator 3 for a methyl 1 carbon. The locator 3 is telling me where I should place an extra carbon. Okay? The alkene we defined as positions 1 and 2. So if I'm going to go through and number this is carbon 1, that is carbon 2, which means that is carbon 3. Which therefore means that's where the methyl is. Do I have a methyl group there? No. Could I just put a carbon there? No, why not? I see the octet. Again, placing those hydrogens was a bad call. Those hydrogens prevented me from building larger, more important things on top of this structure. Okay? So I could go through and now put in that carbon. Okay? Do I now have a structure that represents the name? Yeah. So what we've gone through within this work, and if we push this all the way out, we could simplify this all the way down into that structure. Right? Simplified, we removed all the hydrogens, we implied our carbons as points, and we now have a beautiful looking drawing. If this is a multiple choice test, we're now being asked which of our answer choices match.
Can we assume that pretty much any double bond between carbon is an alkene? Is that how it works?
Yes.
Okay.
All carbon-carbon double bonds are alkenes. Is that a question or you got? Question, go for it.
Not a cheat sheet, but like a paper of like really just the functional groups memorized.
It looks like you found it.
Yes.
It's on the
terrible.
slides.
And then like I realized a lot of them just look the exact same, and I was like, I didn't really pay attention until now. That was my question: was how do you even name them? And I realized that's how. And I realized it looked terrible. And I'm like, I feel like it's gonna be really hard to memorize from this.
I completely agree. I think it's very hard to memorize. Okay, so let's rewind back to my first OChem 1 experience. Guess what happened? I failed. Or rather, I didn't fail. I realized I was going to fail and withdrawed early enough, or withdrew early enough to not achieve a failing grade. Right? And then I went back and I took OChem a second time. Okay? In that second time, I did much, much, much better. I think I did it with a B+. I was at 10 points of an A, which was, it is what it was. Okay? And it is what it was for a very particular reason. Roughly 10% of the class was nomenclature. When I went back and took OChem the second time, I looked at it and said, what do I think is the most important and relevant thing to get out of this class? Okay? And that's what I studied. The things that I decided were not important or relevant, I ignored. Guess what I ignored? Nomenclature. So when I came up 10 points shy of an A, I accepted it. Because I decided to not study nomenclature. That's why I lost 10%. There was my A. Made perfect sense. Okay? How important is nomenclature? It depends on different classes. I'm convinced that it's not important, so it doesn't make up 10% of the grade. Okay? Because I don't think it's appropriate to lose an A because you don't know how to name compounds. I think that's insanely stupid. Okay? But is it important to be able to recognize all those pieces? Yes. How are you going to do it? Sitting and memorizing flashcards? No. It's going to be practice. Drawing out the structures, working through those, doing the really painful thing of, oh my God, I have no idea what this is. How do you figure it out?
Cry.
Do it again.
You can ask questions, and believe it or not, I will probably help you with that, but I need to be careful with that and actually at some point be like, no, I'm not going to help you with that because you have another solution. What's the other solution?
Tutor. Just go review your material.
Look up your notes. Using Dr. Google as well isn't looking at your notes. That's having Google tell you the answer. All you've done is created a bad connection that's going to prevent you from answering questions further on down the road. Looking at your notes is painful. It sucks. You don't like looking at your notes. But that painful and it sucks does what?
Makes you stronger.
Causes you to memorize the content better. Whereas if you just went out and used Dr. Google, you didn't have any negative emotional response to that. It was like, woohoo, I got the answer, right? And everything's fine and dandy until the exam rolls around and you're like, I have no idea what to do. Because you don't know what to do. Google knows what to do. Okay? So you have to spend some of that struggle to go out and look things up. And if you don't know where to look, that's an entirely separate issue. But as we just addressed here, we do know where to look. We do have that awful looking diagram, and we would have to piece through that and be like, an ester, I don't think the ester's on the list.
It's not.
Damn it. Oh well. It's in the textbook though. An ester looks like that. Should I be using ester rules for an alkene? No. Wrong. Okay, which becomes the other part that people fear when they deal with homework. Like, well, I got it wrong. That must mean I'm doing horrible. No, you got it wrong. You've learned what path to not take. That is very valuable. Use that. Because if you don't find the paths that you shouldn't take, guess when you will find them? On an exam. So find them now. Find why you suck at this now so that you don't suck on the exam. That's mean, I know. Okay? But it's not mean. It's telling you to deal with the struggles. You're doing it right. Keep struggling. Don't struggle and run into a wall and just give up. Ask for help, and I can help direct you around some of those impediments. Impediments? One of those words. Okay? But yes, that diagram looks awful. It has a whole bunch of extra information in it, and it's easy to memorize it. Okay? Which becomes some of the challenges behind it. So we have to be a little bit careful with it. Okay? This is where you would ask questions. So back to my question. Structure in the upper right. Does that match the name? Yeah, break my goddamn pens.
Let's just rotate.
Okay? Because if we go through the same numbering system, isn't this 1, 2, 3, 4, 5? Isn't that methyl at 5? What do you mean, not necessarily? Can you jump in on this one? Because this goes back to your starting question.
Should be right from the top to the left.
There is no left, there is no right, there is no up, there is no down. When we look at that numbering that we've now put onto that structure, okay, was an arbitrary numbering system. When we look at how we number our ring when it comes to nomenclature, the alkene does absolutely get numbered 1 to 2. But it could just as easily have been numbered 1 to 2. Which one becomes correct? When it comes to nomenclature, there is a correct answer, unfortunately.
The one at the top one, 1, 2.
The orange one becomes correct. Why is the orange one correct?
That's for the 3 lantern for the methyl.
Okay. It puts the methyl at 3, so that matches this name. Could I have named it 5-methyl? Because doesn't that result in the same thing? I just number it the other direction? Yeah, I would still be able to get the structure, so does that name equally valid? No.
So it goes from being from arbitrary to important?
This isn't important. This isn't important.
Shortest number of the carbon.
There's rules behind how we number. The number isn't entirely arbitrary. It's numbered in the way that results in the smallest locator numbers through our system. So when we look at our initial drawing trying to reverse engineer the name, the orange numbers give us a 3 locator. The purple numbers would give us a 5 locator. And when we deal with names, we want a single name to represent a compound, not multiple. Because if there's multiple names, if I called it 5-methylcyclopentene versus 3-methylcyclopentene, is it possible you could think those were 2 different things? Yeah, and I need to fix that. I fix that by creating a rule set that makes one of the names wrong. Which means, what do you need to know? What are all the rules? Well, what's the rule that called me Mike? And if you're struggling with that, you're like, oh, Mom, you have a mom. Why are you not called Mike? What's the rule that called me Mike? There is none. It's an entirely human invention. Nomenclature. whether it's Gen Chem or OChem, is an entirely human invention. How do we know what the name is? Because someone established a rule. How do you ensure that you know the rule? You look up the rule. How often do you need to look up the rule? As long as it takes for you to consistently get the name right. Why is that problematic? If you look up the rule book for nomenclature, it's larger than our textbook. Yeah, this is why nomenclature is awful. Okay? There are some consistent rules. You will find them as you go through and deal with nomenclature. I want the smallest locator. Smallest locator, smaller numbers. Why is that important? Organic chemists don't like numbers. Make the number small. Okay? Create stupid things that allow you to come up with that. What if there's a tie in the numbering? Use the alphabet. Okay? Switch to a different ranking system that allows you to do it. Okay? And if you're like, that's just nonsense, that's silly. It's not entirely silly. It makes perfect sense. We want one name to represent one compound. That makes perfect sense. But all the rules that are necessary to create said one name are not fun. And they are very much arbitrary. A single human sat down, maybe even a group of humans, said, these are the rules. Okay? So when it comes to left to right, it's not left to right, it's smallest numbers. Okay? And you've got to make sure that you aren't making simple mistakes within that system. We defined the alkene at 1 to 2. Why couldn't I say the methyl was at position 1 and the alkene was at position 2? There's a priority? You mean functional groups have different values or weights? Yeah. Do you know what that priority is?
It's based on reactivity, right?
No, unfortunately not. It's what's listed on the slide. Someone sat down and said, this is the order of priority I want to do. Did they maybe follow some level of reactivity? Sure. Okay. So you could build it a little bit that way, but that's going to get you into trouble. It's a list. You just follow the list. How do you know what the list is? You looked it up, just like you looked up all the other rules.
Is this
Okay.
just a bunch of arbitrary bullshit that just
Yes.
makes sense in the end? Ish?
No, because it will never make sense. If you're talking to me. Some people say it does.
This is a headache.
Yes.
I mean,
This is why I accepted a 10% loss in my grade. Nope, not going to do it. Okay? What pieces should you be picking up? Is there a list of importance in functional groups? Yes. What is that list? Memorize that. Yeah, you should know that. Okay? You should know where to place those. Okay? We said methyl was 1 carbon. How did you know methyl was 1 carbon?
Those are just
It's just the name.
Meth, F, Pro, A.
It's just the name. We defined meth as 1 carbon. You need to memorize that. Okay? And what he started to list off was perfect. Meth, F, prop, bute, pent, hex. Yeah, hept, oct, non, dec, undec, dodec. Nobody knows after that, right? Tridec, tetradec, pentadec, hexadec. I honestly don't know those ones.
You lost 10%.
Okay? Yeah. That's why. Okay? So you should know those primary prefixes because that can help you categorize it. Do you absolutely need to know how to combine everything to come to a perfect name? Do you want that 10%? Okay, then yes, you do. You're like, nope. Nail down the basics. Okay? One of the things that's nice with multiple choice exams is you can look through it and be like, well, I think the longest carbon chain is 5 carbons. So it should say pent. Does it? Nope. Wrong. I don't care about the rest of the name. It doesn't have that piece. So use the multiple choice to your advantage when dealing with nomenclature. Is that depressing? Yes. It should be uplifting. Use multiple choice to your advantage. Kind of, sort of? Okay. Back to your left-right thing. Let's come up with another one. Yes, when we talk about methamphetamine, that is exactly what they're talking about. They're talking about the addition of a single, technically a substitution, of a single methyl group on pseudoephedrine.
Stupid question. Can you make meth?
Everybody can make meth.
Just sounds teacher.
I mean, if meth has
You're welcome. Longest carbon chain.
Couple.
Okay. Back to your initial question, left to right. 1, 2, 3, 4, 5, 6, 7. I would say it's 7 carbons long. And I would be wrong because I read left to right. I don't read left to right. How do I read? Longest carbon chain. So I got to find wherever the longest carbon chain is. So I might go 1, 2, 3, 4. And at 4, I'd be like, ooh, it branches. I see 3 carbons going to the right, and I see more than 3 going up. So 4, 5, 6, 7, 8, 9. I got 9 carbons going up. So this isn't left to right. This is actually left to right, then up. Okay? So I have to adjust my numbering system for how many carbons are in that longest chain. Okay? Because there is no left, right, up, down. And if I'm given a name that says 9 carbons, what am I more than likely going to do? I'm going to draw 9 carbons left to right in a straight line. Is your answer choice going to show that? Undoubtedly not, because it will be easy for someone to accidentally guess the correct answer if you format it that way. The whole point of a test question is, do you actually know it, not accidental? Which means it is almost always tilted off axis. Okay?
Didn't you read it from down up? Because it also would have reached 9 carbons?
From down up?
Yeah.
1, 2, 3, 4. Oh, it does.
Then
I mean,
wouldn't it have also had the carbon a lot closer to, like to 3 instead of 4?
screw you. One, 2, 3, 4, 5, 6. And I think there's an extra issue here. 8, 9. What's the extra issue? 1, 2, 3, 4, 5, 6, 7, 8. 8, 9. Sorry, I didn't mean to draw that many lines. Thanks for being a jerk and pointing out my flaws.
You're welcome.
Okay? Which of those numbering systems is correct? Okay, well, we know the orange one is wrong, so if I could artfully, carefully erase out of it, I could try to pull that off and pull the orange one out. I can tell you right now I can't. Okay, so we're now dealing with what, red, blue, or purple with our counting.
Red or blue?
How do we decide which of those? And now there's so many numbers up there, it's going to be hard for me to see. The name that we want, so this is, again, one of those nasty rules. Orange is going to be, sorry, we already said orange was wrong. Purple is going to be wrong because when I go through and do purple, I only have one substituent. Okay, which is kind of hard to see, so let me show you the purple chain. Here's my purple chain. So this is generally one of the things I like to do is circle my main chain. When I do the main chain in purple, I only have one thing hanging on it. How do I change the name of my hanger-on? Because that hanger-on has a bunch of carbons in it, right? And I don't want to end it like I did with this one. Ene. Here I'd end it with ane because it's alkanes. How did we know methyl was a substituent and not the cyclopentene? How did we know methyl was a substituent and not the cyclopentene? That YL tells us it's a hanger-on. It's something attached to the main chain. For those people saying it's only one carbon, that only works in this specific case. We need something broader that applies to all systems. So if we looked at the purple one, this group is now a hanger-on. I only have one group as a hanger-on. Okay, now let's backtrack out of this. Go away purple. Okay. And I'm going to do blue because I like blue. Now when I do blue, how many hangers-on do I have? That's more hangers-on. That's a better numbering system than the previous one. Why? Because some dipstick said that's the rule.
So the rule here is to have more hangers?
More hangers. So if you're at a system, and this becomes the issue, if you're at a system where you have multiple different same number chains, how do you differentiate those same number chains? More hangers. If we had that modified, where I deleted those carbons initially, now the purple is the longest carbon chain. I don't worry about the hangers. It's the longest carbon chain. It's only when I achieve a tie am I screwed and I need a new rule. Okay? What if I had done red?
That also works when you have two hangers.
How would it be different than blue?
Squiggly.
We're going to come back to squiggly in a second. That's a slightly harder thing for later in this week.
Different squiggly? The hanger is not the hanger.
Would it change?
No.
It's the exact same. If it's the exact same, does it matter? No. You're going to get the exact same name. So you could name it as the blue chain or the red chain. You aren't going to tell a difference. You would get the exact same name. Okay? Because it's the exact same name, we don't need to stress about it. It's going to result in the exact same name, exact same structure, all of that comes into alignment. Kind of make sense? Okay. Can I talk about some other nomenclature? I hate this subject. Okay. Okay. I want to address squiggly, because squiggly's lovely. I like squiggly. Okay. Can I delete all that?
Yes.
Okay. That was undoable as I started to erase it, just for the record. Okay. Squiggly. Boop, boop, boop. Right? Squiggle. Boop, boop, boop. Are those different?
No.
Why not?
They can rotate.
To the squiggly statement. It's only squiggly because that's the way it was drawn. Can it rotate?
Yeah.
So does squiggly matter?
Not really.
No. Why could it rotate?
It's a 3D space.
I'm going to blame Joshua. Thanks for the alkene. Are those the same?
Yes. They're not the same.
What? What's the difference? Why are these two structures different from each other, or rather not the same is probably a better phrasing, which is I think what you use, so good job, versus blue and green?
The electrons are holding on, the orbitals are holding on tighter.
Whoa, that's a lot of words.
A lot of work, little brain.
A lot of good words.
Thank you.
What electrons are you talking about?
That's my point, I didn't know.
So what's the difference between these two drawings?
One has bonds, one doesn't.
What does that line represent?
One has more bonds.
False connection. That one's going to get you in a lot of trouble. It would be a false correlation. The sun rose, and I've always been alive when the sun rose. So every time the sun rises, I should be alive. It's not going to work always. One day that's going to fail, and then I don't have to worry about it, right? What's the difference? And maybe your statement of more bonds needs more words to elaborate what you mean by more bonds.
That's big words.
Something with sharing or something.
So completely opposite.
Okay, so we're hearing something about octet. You said what I wanted to hear, but we heard some other things. So there may be some issues with dealing with octets. And if we go through and show our octets, remember we have all these lovely implied hydrogens that I really did not want to show. But it's fair. I'm not going to show H's all the way through these for the record. Okay? And if we go through and do that, that's where I think we can run into issues with bonds. the number of bonds. Okay, that's just why I don't like that, because you could start referencing hydrogens. Octets. Do both of our structures have octets?
Yes.
Yes. Okay, so octets aren't relevant. Jazz? Say it again.
I was thinking that because of double bond, the structures automatically go into the right?
Took a step beyond orbitals and added a letter. Okay, we've got a double bond. Okay, I would argue it's not a double bond. It is the combination of two bonds. The combination of two bonds is what changes our ability to be more squiggly or not. Okay? That squiggliness has to do with what kind of bonds are being used in that middle section. Okay? All connections start with a particular type of bond. Sort of elaborate. What do you mean S? Begins with S. Did you watch further along? They tend to use s orbitals. They're sigma bonds. So every connection between every single atom will always start with a sigma bond. Okay? Why do we call it a sigma bond? Sigma begins with S, and S-type orbitals are used to make those bonds. Okay? And S-type falls into hybridization, which I believe is later in the week, and everybody probably got hung up on nomenclature. Okay? So one of these bonds is a sigma bond using S-type orbitals. To get a double bond, though, I need more electrons in that space. That becomes problematic, because if I put more electrons into the same space, what happens? How many electrons can an orbital hold?
2.
2. What happens if I try to put 2 more electrons into that same space? Not going to happen. It pops out, and yet somehow I get a double bond. Instead of using my S-type orbitals, I use my P-type orbitals, generating a pi bond. The double bond is composed, that's what I want, a sigma and a pi bond. Okay? The sigma bond involves S-type orbitals, and our pi bond involves P-type orbitals. Those have drastically different energetics, and they have drastically different appearances. Okay? That mathematical probability appearance is what changes the ability to switch between squiggly flop all over the place and now locked in space and it cannot move. Okay? Which is why Joshua was correct when we looked at these two. They are not the same, whereas our blue and green are the same because they're only connected by sigma bonds. Those sigma bonds have the ability to freely flip and rotate. Right? Very, very simple analogy for this, but if let's look at a sigma type bond, we said S-type orbitals, let's pick the extreme, let's do an S orbital and an S orbital. Would I expect a bond between those two S orbitals? What does it mean to be a bond? Sharing of electrons. How do we know where our electrons are with this depiction? Say it again?
As I say, I guess you don't need to have to connect.
Sorry, getting at the right idea. Where are the electrons in my S orbital here?
Right on the outside?
No. What is an S orbital?
It's a space.
It's a space where our electrons exist. Where? Everywhere within it. If I'm going to share electrons from this atom to this atom, that black dot representing our nucleus, what has to happen to the orbitals?
They need to intersect.
They need to overlap. So at this point, I don't have a bond. When I overlap it, we'll draw a different color. Whoop. What have I now shown in that intersection?
Electron share.
Electron sharing. Now I have the potential for a bond. Okay? Ta-da! And because I used S-type orbitals, I'll call that bond a sigma bond. Okay? Here's the fun thing with this. If we were to now draw a line, right? I've got a line connecting them. Okay? It's like my pen. I've got a ball on this end and a ball on this end, and those two balls have to directly overlap, right? What happens if I rotate one of the balls? Do they stay overlapped? Yeah, remember they pass through each other. It's hard to do with physical objects because physical objects don't pass through each other. But we're talking about two balls, and I just rotate them around. Yeah. Okay? Around that bond axis, yeah, they stay overlapped. What changes when we move to a pi bond? What is a pi bond made of? What's that?
P orbitals?
P orbitals, and there's 3 different orientations for p orbitals. When we talk about the pi bond, we need to now look at how it can overlap. Okay? Our simplest approximation, right, if we look at that p orbital, it's now going to be sitting kind of directly on top and below our dumbbell shape. The sigma bond is now made, which means do the pi bonds ever overlap? Or p orbitals ever overlap? No. Why is that a problem? If they never overlap, you can't form a bond. Okay? But electrons are really, really, really tiny. And what can electrons do in this weird, multiverse of life?
Do an indirect bond.
They do what's known as an indirect bond. They can quantum tunnel. They can jump from one space to another space without passing through the intermediary. And if that blows your mind, take a peek at it. Right? Ultimately, what we're saying is as long as those 2 p orbitals are close enough to each other, the electron can be like, whoop, jump to the other side. If it has jumped to the other side, what is it by definition done? They shared. Well, if the electrons have shared, what have we done? We've created a bond. We've negated the overlapping issue because where are our p or our p electrons? They're above and below. Above and below what? The s orbitals hovering in the middle. So if we combine all of these things together, the electrons of our sigma bond are chilling in here. The electrons of our pi bond are chilling at the top and the bottom, which means the electrons are not occupying the same space. We fixed the problem. I can now put more electrons into that space and create a larger bond.
What's up with the electron just magic?
Yep, that's your answer. That's the answer as far as the class is concerned. Yep.
That's it. That's all you got. You can't.
Heisenberg uncertainty principle, do you understand anything about Dirac equations or wave functions? No. Anything I say is nonsense. Magic.
You said something about quantum.
Yes.
At magic.
Because it's, yep.
Everything is,
Anything you want to have happen, call it quantum and it happens. Okay? This is ultimately what's happening is your electrons have been provided close enough space that they can tunnel through an existence of non-existence. And they can exist in both spaces. This allows us to generate those 2 bonds. Why does this contribute back to this whole squiggly versus not squiggly thing?
because some can look squiggly because they just normally are, and some can look squiggly because they're.
The sigma bond, what happens when I rotate? To the overlap of those orbitals. They're still overlapped. P orbitals. What happens when I rotate? They no longer overlap. That's why double bonds don't rotate, because for them to rotate, you've broken the overlap. There's no more double bond. The only reason we have a double bond is because of that orbital overlap. Crazy. Which means what do we need to understand? We need to know atomic orbitals. We need to know molecular orbitals. We need to know p orbitals. We need to know s orbitals. We need to learn about hybridization, a whole other level of magicness. Right? And what we're trying to do is describe our atomic structure with where all our electrons exist. We have theoretically basic knowledge of sp orbitals from Gen Chem. Right? And we say, how do those sp orbitals apply to molecules? Well, right out of the gate, they don't. Because when we talk about s and p orbitals, what are they?
Atomic structures?
They are, yes, what's that first word? Atomic structures. And why does that become a problem when we now move to molecules?
We made out of a bunch of atoms?
They're not atoms anymore, they're molecules. You've changed that basic fundamental structure, which means you have to change how the electrons exist. This is why we move into molecular orbitals instead of atomic orbitals. This is why we need hybridization theory to explain bonding patterns. This is why we need molecular orbital theory to help explain where the orbitals are, where the electrons are, and why things can rotate or not rotate. It's amazing. And in the vast majority of cases, I will also say it probably just goes straight over your head, and that's okay. Right? What we're trying to do is recognize the important features behind those. P orbitals, when you have pi bonds, don't rotate those bonds. Sigma bonds, you can rotate. This is why I balk in the videos, and instead of calling them sigma and or single and double bonds, you usually hear me reference them as single and multi-bonds. Why am I calling it multi-bonds? It sounds stupid. Nobody calls them multi-bonds. Because nobody calls them multi-bonds, and double bonds is a false presumption. Double bond makes it sound like it's this whole new one thing. It's not one thing, it's two things. It's a single bond and a pi bond, a sigma and a pi. You need a new language system to describe that bonding pattern, and that's fun. Do you want to go back to nomenclature?
Tired.
I don't blame you. Still got 5 minutes.
I've never seen someone like ramble on about trying to teach how left and right doesn't really
Ramble?
exist. Ramble is an understatement,
Ramble.
sir. Understatement of the year.
We perfectly described the systems that we're going to have to be dealing with, which means we don't have those left and rights, and we have to forget them. We also have to remember them when we deal with computers, which is unfortunate. All right, so we did a little bit of nomenclature. We did a little bit of more fun stuff, the sigma and molecular orbital stuff, which you got those videos coming in at the end of the week. So you can come in Wednesday and be like, whoa, okay, maybe you're making sense. Or you can just be like, you need to do it all over again. Yeah, Jazz.
Does Vesper basically has to do with the
Where did I want? I thought I had a thing on Vesper. I didn't pull it up. So what Vesper is going to address is pushing back to kind of the reality. So when we look at Lewis structure for methane would keep us happy with this. Okay, we go, oh, okay, that's fine. And we go, well, is that an accurate representation of the three-dimensional molecule? Okay. The way it looks is that the bond angles there would all be 90 degrees. Okay. Well, if those are all equivalent bonds, they're all still carbon and hydrogen, shouldn't all the bond angles be identical? Are they all 90 degrees? What about that bond angle? That looks like 180, which means this representation doesn't work very well. Okay? And this is where Vesper came in. Vesper comes in and says, okay, well, if we look at this, those all need to be equivalent, so what we're going to do is treat them as we would. Okay? Each of those lines represents electrons, and electrons are going to repel away from each other. If I have 4 groups of electrons and they repel away from each other, what shape do they make? Tetrahedron. If you don't know what that is intuitively, just because you're like, oh, no one does. Well, maybe some people do. I don't. Okay? What you'd be expected to do is just memorize it. That's the shape that comes out of it, is tetrahedral. So if we're now going to convert our Lewis structure into something that more accurately reflects the three-dimensional space, what we'll note is that we have to, and calling it a type of bond is a bit of a misnomer here, a new way to describe the bonds. What we introduce is this wedge in the dash. The wedge meaning it gets closer to you, it's coming out of the plane, and the dash meaning it goes into the plane, okay, it goes behind us. What do the solid lines mean? They're in the plane of the paper. This now better represents the three-dimensional model. Okay? Why do I want that? Well, everything about OChem is how those pieces fit together in a three-dimensional world. Okay? We talk about just an individual human. If my arm is coming out of my forehead, you interact with me differently. Okay? So where those pieces are located in three-dimensional space does become very important. Just in human interactions, throw it in with chemicals, and now things go completely haywire. So we really need to understand that three-dimensional space. How important is it to specify that three-dimensional space? That changes, okay? Because if we go through and look at these, you'll note I haven't shown wedges and dashes on any of these structures. Officially, these two, these two, oh, that's a horrible arrow to use. These two don't need wedges and dashes. This one does. Why did I not show wedges and dashes on it? What's that?
Connected.
It would make it look gross. Like, that's about it. I don't want to have to add a whole bunch of hydrogens with wedges and dashes because it looks gross. It makes it more difficult to interpret. So depending on what I want to do, I may or may not choose to include them, which again means you have to be able to decide when and when not to show it. Okay, when it comes to smart work, when do you show it? When it asks. Okay, when do you not show it? And when it doesn't say anything about it, don't show it. Okay, and we'll encounter a little bit later in the semester a subject known as stereochemistry, and stereochemistry does require the use of wedges and dashes, okay? Which is getting back to this concept of, are these two drawings the same or not? And what we'll find is wedges and dashes mess that whole world up with three-dimensionality, which is why we need to be aware of it. Yes, sir?
Oh, I just want to clarify, so it sounds like a dumb question after all
No.
this, but the wedge means it's coming towards me, like in a 3D space.
Yep.
And then the dashes mean it's going like behind,
Yep.
opposite. I just wanted to make sure
Yep.
of that.
Nope. It's absolutely right. So all we need to be aware of is that it exists, okay? What's going to happen is we'll have to layer other information on top of it, okay? If we bring in the orbitals that we were just talking about, one of the things we'll encounter is that carbon, if we look at its bonding pattern, the electrons around it, we know this is a three-dimensional object. Could I explain the existence of those bonds using carbon's atomic orbitals? Well, what are the atomic orbitals I would expect carbon to be using in a bond? It was last week. You guys answered it last week. Like, phew.
Fried.
It's Monday, not Friday. It's Tuesday, sorry. What electrons would we expect carbon to use to be making those bonds? Where are those electrons located?
The ownership?
The valence electrons, our outer shell. Okay, keep going. What are those electrons?
The outermost electrons?
Where are they? Which s orbital? Not the 1s orbital. The 2s orbital. The 2s orbital looks like a circle. Those of you being, doesn't the one, yeah, it does. It's just a smaller circle. Is it just the 2s orbital? No, what else does it have? Two p orbitals. We have the two p's, okay, which we could draw, and that's my horrible representation of a one coming out of the plane at you. Okay? What are the angles between all of my p orbitals? 90 degrees. Does that immediately throw problems into our understanding of the existence of our molecules? What is the bond angle in a tetrahedron? 109.5, also known as not 90. Okay? Which means the atomic orbitals don't properly explain how we can get the molecule. This is why we have to morph our atomic understanding using different theories. Hybridization theory does a really good job of doing that, saying, I got 4 equivalent orbitals, I have 4 atomic orbitals. They're just probabilities anyway, let's just mash all the probabilities together and make new ones. Yep, that's how we do it. Okay? Or linear combination of atomic orbitals, molecular orbital theory, which is a fancy way of saying, do you have a supercomputer? If the answer is no, don't worry about it, for the most part. Okay? That's kind of the point of VSEPR, is it's taking Lewis structure. Do I understand the basic bonding patterns? How do those relate to the real world three-dimensional space? dang, once I'm in the real world three-dimensional space, all of that stuff I learned in Gen Chem doesn't apply, sort of. It doesn't apply because it's a different system, molecule versus atomic. So how do we tweak the atomic to match the molecule? Once we've matched the molecule, what have we done? We can now say where the electrons exist around the carbon. Why is that important? When I run a chemical reaction, how do I know I have a bond? How do you know you have a bond, period?
New stuff.
New stuff isn't quite descriptive enough. What do you got, Jazz?
Say connection or charge.
Atom A, atom B. How do I show that there's a bond between them? I show a line. What's the line?
Electrons,
Electrons. Where do electrons exist?
the outermost shell. Carbon.
On an atom. They exist in molecular orbitals. If I want to run a chemical reaction where I say take C and I want C to make a bond with A, what has to happen? What am I moving with those red arrows? Electrons. I can only move them if I know where they are. That's why we need molecular orbital theory to help explain that, to set that up so that we can start that fundamental approach. Fun.
So it's kind of like resonance.
Ah, it is exactly like resonance, okay, which is kind of where we'll end. How is it a big difference from resonance?
Not showing any electrons within.
No, resonance will still show our electrons moving around. Resonance only changes the electrons within a molecule. When we run a chemical reaction, by definition, it is
Outside.
multiple molecules, okay? Or potentially cleaving sigma bonds if we're going to look at a decomposition, and making multiple molecules. So resonance is all about moving non-bonding pairs and pi bonds. If you don't have those, you can't do resonance. Chemical reactions are about moving, at its simplest level, sigma bonds. Because the instant I break a sigma bond, I've now broken an atom away from another atom. That's a chemical reaction. Right? So I have to understand, again, where those electrons are, why they are where they are, how they displace within a molecule or within a bond. All of those things stack and build. So again, what we are looking at is the basic fundamental structure. We now have atoms connected by lines. What do those lines represent? Those represent electrons. Those electrons represent orbitals. Well, what are the orbitals that contain those? Once I know those orbitals that can contain those, I can now step back and look at larger properties, spins, bond rotations, or lack of rotation. Right? I can now change my view on the molecule. Does that change how I draw it? Yeah, so we need those new drawings to appear. Once we got all that, then it's easy. Okay, I need to stop.